The universe is vast, filled with wonders that boggle the mind and mysteries that defy explanation. But our solar system, the cosmic neighborhood we call home, is no less enigmatic. What if I told you that the planets, moons, and even the empty stretches of space between them hold secrets so puzzling, they continue to elude the sharpest minds on Earth? From the perplexing dance of Venus spinning in reverse to the eerie whispers of methane on Mars, our solar system is like an unfinished book, each chapter more baffling than the last. In this video, we're diving into 25 of the most intriguing, unsolved mysteries lurking within our celestial backyard. Some might make you rethink what you know, others might ignite your curiosity to explore further. But all of them reveal just how little we truly understand about the cosmic puzzle we're a part of. So buckle up, because this journey into the unknown is just getting started. Now turning to the first mystery, the very origin of our solar system itself remains one of the most fascinating puzzles in astronomy. Scientists widely accept the nebula hypothesis, which suggests that about 4.5 billion years ago, a massive cloud of gas and dust began to collapse under its own gravity, forming the Sun at its center and eventually the planets, moons, and countless smaller bodies around it. While this theory gives us a broad framework, it is far from complete. Key questions linger, like what triggered the initial collapse of that primordial nebula. Was it a shock wave from a nearby supernova or something else entirely? And even if this explains the Sun's formation, how did the planets fall into their near-perfect orbits? Why do some celestial bodies, like the gas giants, form farther out, while rocky planets like Earth occupy the inner regions? One of the biggest gaps in our understanding lies in the chaotic early period of the solar system. During this time, collisions, migrations, and gravitational forces all played a complex role in shaping the arrangement we see today. For instance, some models suggest that Jupiter may have wandered inward before moving back out, disrupting other planetary formations in the process. It's also unclear how smaller bodies like asteroids and comets managed to survive this violent era intact. Could they hold the key to understanding the solar system's infancy? The more we learn, the more questions emerge, reminding us just how much of this cosmic origin story remains unwritten. Moving forward, let's unravel another enigma, the perplexing heat of the Sun's corona. Moving forward, let's dive into one of the Sun's most baffling secrets, the enigma of its corona. The Sun's corona, its outermost layer, burns at an astonishing temperature of over 1 million degrees, while its surface, known as the photosphere, hovers around a much cooler 5,500 degrees. This creates a paradox. How can the outermost layer, farther from the Sun's core where nuclear fusion occurs, be hundreds of times hotter than the surface itself? Scientists have proposed several theories to explain this mysterious phenomenon. One leading theory suggests that magnetic waves, known as Alfvén waves, may carry immense energy from the Sun's interior and deposit it in the corona. Another hypothesis focuses on nanoflares, which are tiny, rapid bursts of energy that could collectively heat the corona to its extreme temperatures. Additionally, plasma interactions and turbulent magnetic fields might play a role in creating and sustaining this intense heat. However, none of these theories fully account for the observed temperatures or the exact mechanism behind this energy transfer. What adds to the intrigue is that this phenomenon complicates our understanding of stellar physics as a whole, not just the Sun. If the mystery of the Sun's corona were solved, it could unlock crucial insights into the behavior of other stars in our galaxy and beyond. Despite significant advancements in solar observation, particularly from spacecraft like the Parker Solar Probe, which is currently studying the Sun closer than ever before, this paradox remains unresolved. For now, the Sun keeps its fiery secret well guarded. As the next challenge unfolds, we journey beyond the Sun to uncover the strange gap in the Kuiper belt, aptly named the Kuiper Cliff. As the next challenge unfolds, we journey into the farthest reaches of our solar system, beyond the orbit of Neptune, where an enigmatic feature known as the Kuiper Cliff awaits. The Kuiper Belt, a vast collection of icy bodies and dwarf planets, is expected to gradually thin out as it extends outward. However, scientists have stumbled upon a puzzling surprise beyond a certain point. The density of these objects drops off suddenly and dramatically, creating what we call the Kuiper Cliff. This sharp decline defies what mathematical models predict, leaving a gaping question. Why does this abrupt edge exist? Some theorists suggest the presence of an unseen celestial body, perhaps a massive planet hiding in the shadows, whose gravitational influence could be sculpting the Kuiper Belt in this unusual manner. Others speculate that the abrupt drop might be the result of gravitational waves or disturbances caused by neighboring stars in the early history of our solar system. Yet another possibility involves interactions with the galactic tide, the gravitational forces stemming from the broader Milky Way galaxy itself. Despite these intriguing ideas, no definitive evidence has been found to fully explain the Kuiper Cliff, and the search for answers continues. This mystery not only deepens our curiosity about the outer regions of the solar system, but also challenges our understanding of planetary formation and the underlying dynamics of celestial mechanics. As we leave this icy frontier behind, our journey pivots back toward Earth to explore its most life-sustaining feature, water, and the perplexing mystery of where it truly came from. Now turning to our own planet, we delve into one of the most profound and enduring mysteries, the origin of Earth's water. Water is the cornerstone of life as we know it, covering over 70% of our planet's surface and existing in rivers, oceans, glaciers, and even as vapor in the atmosphere. But here's the puzzle: where did all this water come from? Scientists have long debated its true origins. One prominent theory suggests that water was delivered to Earth during its early formation through the impact of icy comets. These frozen wanderers from the outer solar system are rich in water, and their collisions with our young planet could have deposited significant amounts. Another leading idea points to asteroids, specifically carbonaceous chondrites, which contain water-bearing minerals. These asteroid impacts might have supplemented Earth's water supply, especially during a chaotic early period known as the Late Heavy Bombardment. While both scenarios are fascinating, neither fully accounts for the vast abundance of water on Earth today. Chemical analysis of Earth's water reveals subtle differences in isotopic ratios when compared to the water found in comets and asteroids, leaving gaps in these explanations. To complicate matters further, some scientists posit that water may have been trapped within Earth's mantle during its formation, gradually released through volcanic activity over billions of years. This raises even more questions about the primordial solar system and the unique conditions that made Earth so hospitable to life compared to other planets. Despite extensive research, the origin of Earth's water remains one of the most compelling unsolved mysteries of planetary science. It is not just a story of geology and chemistry, but a tale intricately linked to the origins of life itself. From this life-giving mystery, our exploration now shifts to one of our planetary neighbors, where a puzzling question about a planet's unusual spin continues to baffle scientists. Let us journey to Venus and uncover the enigma of its retrograde rotation. Moving forward, we arrive at Venus, a planet often referred to as Earth's twin due to its similar size and proximity. Yet, Venus hides a mystery that sets it apart from nearly every other planet in the solar system: its retrograde rotation. Unlike Earth and most of its planetary siblings, Venus spins backward, meaning that if you stood on its surface, you would see the sun rising in the west and setting in the east. To add another layer of peculiarity, Venus rotates incredibly slowly, taking over 200 Earth days to complete just one rotation. But why does Venus spin this way? One of the leading theories suggests a colossal collision early in its history. scientists hypothesize that a massive object may have struck Venus, disrupting its original spin and forcing it into its current retrograde motion. This idea is supported by similar scenarios thought to have shaped other celestial bodies, like the Moon's formation after a giant impact with Earth. However, no definitive evidence of such a collision has been found on Venus, leaving room for alternative explanations. Another intriguing possibility involves the planet's thick atmosphere, which is over 90 times denser than Earth's and composed mostly of carbon dioxide. Some researchers propose that atmospheric dynamics, combined with gravitational interactions with the Sun, could have gradually reversed Venus's rotation over time. This theory emphasizes the complex interplay between a planet's surface, atmosphere, and external forces, painting a picture of Venus as a world shaped by extraordinary processes. Despite these compelling ideas, no single explanation fully accounts for all the observed characteristics of Venus's spin. Understanding this enigma is more than just solving a cosmic puzzle. It provides insights into the diverse ways planets evolve and the delicate balance of forces that govern their motion. As we leave Venus's strange behavior behind, our journey continues to a familiar giant where a centuries-old storm has refused to fade. Let us set our sights on Jupiter and unravel the secrets of its iconic Great Red Spot. With the next phase of the journey in sight, we arrive at Jupiter, the king of planets, home to one of the most iconic and enduring mysteries in the solar system, the Great Red Spot. This massive, swirling storm has raged for at least 400 years, a longevity that defies explanation when compared to weather systems on Earth, which last only days or weeks. Stretching over twice the width of our planet, the Great Red Spot stands out as a testament to the immense power and complexity of Jupiter's atmosphere. But how has this colossal storm persisted for so long? Scientists theorize that Jupiter's lack of a solid surface plays a major role. Unlike Earth, where friction with the ground eventually dissipates storms, Jupiter's gaseous composition allows its weather systems to roam freely across the planet. Additionally, the rapid rotation of Jupiter spinning on its axis in just under 10 hours creates intense jet streams that may help sustain the storm's energy. Another fascinating aspect is the Great Red Spot's altitude. It sits higher in the atmosphere than surrounding clouds, leading researchers to believe that vertical energy transfers might contribute to its survival. Despite these insights, major questions remain. For instance, why is the storm shrinking? Observations in recent decades have shown it gradually getting smaller, yet no one knows for certain if this signals its eventual disappearance or a natural phase in its evolution. Furthermore, the striking red coloration of the storm also remains a puzzle. Some suggest that sunlight interacting with certain chemicals in Jupiter's upper atmosphere creates this hue, but the exact composition of these materials is still unknown. Ultimately, the Great Red Spot isn't just a mystery about weather. It's a window into the dynamics of gas giant planets and the forces that shape them. As we leave this stormy titan behind, we turn our focus to Mars, where an absence of something just as vital as atmosphere presents its own set of unanswered questions. Let us uncover the mystery of Mars' missing magnetic field. Now turning to Mars, the red planet, we confront a mystery that strikes at the core of its identity quite literally. Unlike Earth, which is protected by a powerful magnetic field generated by the movement of molten iron in its core, Mars has no such shield. This absence has left its atmosphere vulnerable to the relentless assault of solar winds, leading to its gradual erosion over billions of years. But the real question is, why did Mars lose this critical magnetic field in the first place? One leading theory suggests that Mars' core cooled too quickly. On Earth, the churning of a molten outer core around a solid inner core drives the dynamo effect, generating our magnetic field. Mars, being a smaller planet, likely cooled at a faster rate, causing its core to solidify and halting this essential process. Without its magnetic field, Mars' atmosphere was stripped away, leaving behind the cold, barren desert world we see today. Another theory posits that catastrophic asteroid impacts may have disrupted the magnetic field. Early in its history, Mars experienced massive collisions, and some scientists believe these impacts could have temporarily halted or even permanently destabilized the core's movement. Whatever the cause, the consequences have been profound. The lack of a magnetic field not only robbed Mars of its ability to retain a thick atmosphere, but also diminished its capacity to support liquid water on its surface for extended periods. This directly impacts the potential for life, both past and present, as any organisms would need to endure extreme radiation and harsh conditions. Even more intriguing is what this could mean for future human exploration. Without a magnetic shield, any colonies on Mars would be directly exposed to harmful cosmic radiation, presenting a significant obstacle to long-term habitation. The mystery of Mars' missing magnetic field is not just a question of planetary science. It holds the key to understanding the planet's past, its potential for life, and its future as a possible second home for humanity. Moving forward, we set our sights beyond Mars, venturing into the far reaches of the solar system where whispers of an unseen guardian beckon us to unravel the enigma of Planet 9. With the next phase of the journey in sight, we find ourselves drawn to the outermost edges of our solar system, where an invisible enigma lurks in the shadows. Dubbed Planet 9, this hypothetical world has sparked intense curiosity and debate among scientists. The story begins with peculiar gravitational effects observed on distant objects in the Kuiper belt, the icy region beyond Neptune. These objects exhibit orbital patterns that seem to defy explanation, as though pulled by an unseen celestial body. Could this be evidence of a massive, undiscovered planet hiding in the farthest reaches of our solar system? Researchers estimate that if this planet exists, it would be several times the mass of Earth, located at an extraordinary distance, so far that it would take tens of thousands of years to complete a single orbit around the Sun. Yet, despite its potential size, Planet 9 has eluded direct observation, even with our most advanced telescopes. Why is that? One possibility is that it may be extraordinarily faint, reflecting very little sunlight due to its immense distance and possibly being shrouded in a cloud of gas or dust. Another theory suggests that its orbit could position it in a part of the sky that has been difficult to survey, perhaps lying near the Milky Way's dense star field, where it would be camouflaged by the brightness of countless stars. And then, of course, there is the chance that Planet 9 doesn't exist at all, and the gravitational anomalies could instead be explained by a yet-to-be-discovered framework of physics or the collective influence of smaller, unseen objects. The mystery of Planet 9 captivates not only because it challenges what we know about the solar system, but also because of what it represents: the possibility that even in our own cosmic backyard, there are still monumental discoveries waiting to be made. With each new study and each fleeting hint of its presence, the search intensifies. So, for now, Planet 9 remains a tantalizing ghost of the solar system, a reminder that the universe often keeps its secrets hidden in the most unexpected places. As we leave behind this distant intrigue, our journey turns back inward to a place where Saturn reveals a stunning and mysterious geometric phenomenon, its iconic hexagonal storm. With the next phase of the journey in sight, we delve into one of the most striking and perplexing features in our solar system, Saturn's hexagonal storm. Nestled at the gas giant's north pole, this massive geometric formation has baffled scientists since its discovery. Spanning over 20,000 miles across, the hexagon is big enough to fit nearly 4 Earths inside it, and yet, despite decades of study, its origins and behavior remain shrouded in mystery. The sheer stability of the hexagon is extraordinary. Unlike storms on Earth, which shift and dissipate over days or weeks, Saturn's hexagon has persisted for at least 4 decades, possibly much longer. But how does such a perfectly six-sided structure form on a planet dominated by swirling gases? One leading theory involves atmospheric wave patterns. Some scientists believe that the hexagon could be a manifestation of standing waves, which are stable, repeating patterns created by differences in Saturn's wind speeds at various latitudes. Imagine a jet stream on Earth, but far larger and faster, creating ripples in the atmosphere that somehow lock into this peculiar hexagonal shape. However, even if this theory holds, it doesn't fully explain why the hexagon has remained so stable or why its sides are so straight. Another possibility is that the shape is influenced by deeper forces within Saturn's interior, where unknown dynamics could be shaping the atmosphere in ways we haven't yet understood. The storm's persistence and symmetry challenge everything we know about fluid dynamics and planetary weather systems. Adding to the intrigue, the hexagon isn't just a flat, two-dimensional feature. Recent observations suggest that it extends deep into Saturn's atmosphere, like a colossal column of swirling gases. And then, of course, there's the eerie fact that Saturn's south pole, in stark contrast, features a completely different structure, a massive swirling vortex without any hint of geometric patterns. Why does the North Pole display such striking order while the South remains chaotic? Could this be a clue about the planet's deeper mysteries, or is it simply a quirk of atmospheric conditions? These questions remain unanswered. What we do know is that the hexagon stands as one of the most vivid reminders of how much we have yet to uncover about the planets in our solar system. As we look closer and probe deeper into these enigmas, we are reminded that even the most familiar celestial neighbors can still hold secrets that defy explanation. Moving forward, our attention turns to another planetary puzzle, Mars, where transient methane spikes spark questions about the red planet's potential for life. Now turning to the next enigma, we arrive at Mars, a planet that has fascinated humanity for centuries. One of its most intriguing mysteries lies in the detection of methane, a simple yet compelling molecule that could hold clues to the possibility of life. Methane is of particular interest because on Earth, it is often linked to biological activity. However, it can also be produced through geological processes, like the interaction of water with rock or volcanic activity. On Mars, transient spikes in methane concentration have been detected by orbiters and rovers, but the source of these emissions remains a puzzle. The methane appears to fluctuate in unpredictable ways, with higher levels detected during certain seasons or in specific locations. What makes this even more baffling is how quickly the methane seems to disappear from the Martian atmosphere. On Earth, methane can linger for hundreds of years, but on Mars, it vanishes in a matter of months. This rapid disappearance suggests there may be unknown processes at work, perhaps involving the planet's surface or even its thin atmosphere. One theory is that the methane could be produced by subterranean microbes, living deep below the surface where they are shielded from harsh radiation. If true, this would be a groundbreaking discovery, indicating that Mars might still harbor life today. Alternatively, the methane could result from purely geological processes, such as reactions between olivine, a common mineral on Mars, and liquid water trapped beneath the surface. Yet, neither explanation fully accounts for the observed variability or the seasonal patterns. Complicating this further is the challenge of accurately measuring methane on Mars. Instruments aboard rovers like Curiosity have sometimes reported spikes, while orbiting spacecraft have detected little or no methane at the same time. This discrepancy suggests that methane may be highly localized or that current detection methods are not sensitive enough to capture its elusive behavior. The mystery deepens when considering Mars's history. Billions of years ago, the planet was warmer and wetter with conditions that might have supported life. Could the methane we detect today be a vestige of ancient biological activity, slowly seeping to the surface from long-buried reserves? or is it an entirely modern phenomenon, hinting at active geological or even biological processes occurring right now? Until we can gather more data or devise new ways to directly study the Martian subsurface, these questions will remain unanswered. For now, methane on Mars continues to serve as both a tantalizing clue and a reminder of how much we still have to learn about the red planet. As we leave the dusty plains of Mars behind, our journey takes us to another frozen mystery, this time orbiting the distant planet Uranus. Its extreme axial tilt, which makes it roll on its side, defying the norms of planetary motion. As the next challenge unfolds, we find ourselves intrigued by the peculiar behavior of Uranus. Unlike other planets in the solar system, Uranus essentially rolls on its side as it orbits the Sun, with an axial tilt of roughly 98 degrees. This bizarre orientation means that its poles take turns directly facing the Sun during its long seasons, each lasting over 20 Earth years. The cause of this extreme tilt has puzzled scientists for decades. One popular theory suggests that Uranus may have experienced a massive collision early in its history, perhaps with a protoplanet or another large celestial object, strong enough to permanently knock it off its original axis. However, this idea raises further questions. If such a colossal impact occurred, why does Uranus still maintain relatively circular and stable orbital characteristics? A collision of that magnitude might have left more noticeable scars, such as a highly eccentric orbit or significant disruptions to its moons. Another intriguing possibility is that a series of smaller impacts, rather than one significant blow, gradually forced Uranus into its unusual tilt. Yet, even this explanation leaves gaps in our understanding, particularly when considering the near-perfect alignment of its ring system and moons with its tilted equator. This suggests that whatever caused the planet to tilt also influenced its entire system, including its satellites and rings, in ways we don't yet fully understand. Some scientists have proposed that gravitational interactions with another large planet or even the early Sun could have nudged Uranus into this position over millions of years. However, these scenarios require highly specific conditions to align with what we observe today, making them difficult to confirm. Further complicating the mystery, Uranus also has an unusually cold and featureless atmosphere compared to its neighbor, Neptune, even though both planets are similar in size and composition. Could this be linked to its axial tilt, perhaps influencing how atmospheric heat is distributed across the planet? Or is this simply a separate enigma waiting for its own answers? To unravel these questions, future missions to Uranus may provide vital clues, potentially offering direct observations of its internal structure, core dynamics, and the history embedded in its moons and rings. These insights might finally piece together the story of how Uranus ended up with such a unique orientation, a story that could reshape our understanding of planetary formation and evolution. With this unresolved mystery lingering in our minds, we now shift our attention to the distant past, to a hypothesis that suggests the solar system once housed an additional terrestrial planet, a world that may have vanished under dramatic circumstances, the case of the missing planet V. As the Sun rises on the next chapter, we delve into the fascinating hypothesis of a lost world, a fifth terrestrial planet, often referred to as Planet V, that may have once existed in the solar system. Scientists have theorized that this mysterious planet could have played a significant role in shaping the arrangement of the planets we see today before being ejected under dramatic circumstances. The idea of Planet V stems from simulations and models of the early solar system, which suggest that an additional rocky planet might have once orbited between Mars and the asteroid belt. According to this hypothesis, Planet V may have disrupted the orbits of nearby celestial bodies, including asteroids and other planets, through its gravitational influence. Over time, the instability caused by Planet V could have triggered collisions, reshaped trajectories, and perhaps even contributed to the formation of the asteroid belt itself. But what could have ultimately happened to this enigmatic planet? One theory proposes that gravitational interactions with Jupiter, the solar system's giant, may have spelled its doom. The immense gravitational pull of Jupiter could have slingshotted planet V out of the solar system entirely, flinging it into the vast void of interstellar space. Alternatively, it is possible that planet V met a catastrophic end, colliding with another planet or a significant celestial body in the inner solar system. Such a collision could explain certain anomalies in the composition of planets or moons, leaving behind clues that we have yet to fully decipher. The absence of direct evidence for planet V, however, keeps this mystery firmly in the realm of speculation. If it did exist and was ejected, it may now be a rogue planet wandering the galaxy, its history forever separated from our solar system. On the other hand, if it was destroyed, remnants of planet V might still lie hidden in the asteroid belt or even within the crust of Earth and Mars, waiting to be identified. Understanding the fate of this potential fifth world not only adds another layer of complexity to the story of our solar system, but also provides insight into the chaotic processes that governed its early days. As we ponder the possible existence and disappearance of planet V, we are reminded of how much remains unknown about the formative years of our cosmic neighborhood. And with that, we turn our gaze to one of Saturn's most curious moons, Titan, a world of methane lakes and a mysterious cycle that raises profound questions about its potential for life. With the next phase of the journey in sight, we turn our focus to Saturn's enigmatic moon, Titan, a world that challenges our understanding of planetary science with its alien but strangely familiar features. Titan is shrouded in a dense orange haze of nitrogen-rich atmosphere, making it the only moon in our solar system with a substantial atmosphere. But what truly sets Titan apart is the presence of vast liquid methane lakes on its surface, a discovery made possible by the Cassini-Huygens mission. These lakes, some stretching hundreds of miles, are part of an active methane cycle eerily reminiscent of Earth's water cycle, complete with evaporation, cloud formation, and rainfall. While this methane cycle is fascinating on its own, it raises deeper questions about Titan's potential for life. On Earth, water serves as the universal solvent, enabling the complex chemistry of life. On Titan, however, methane and ethane exist as liquids at its frigid temperatures, potentially playing a similar role. Could life, as we do not yet understand it, thrive in such an environment? This question remains one of the most tantalizing mysteries in planetary exploration. Adding to the intrigue, scientists have observed an ongoing process that appears to replenish Titan's methane reserves, preventing them from depleting over time. This suggests there could be an underground reservoir or even geological activity driving this replenishment. However, the exact mechanism remains unknown, leaving researchers to speculate. Could it involve cryovolcanism, where icy volcanoes emit methane gas into the atmosphere? Or might there be completely new processes at work that we have yet to discover? Titan's methane lakes also challenge us with their chemistry. At the moon's surface temperature, which is far colder than anywhere on Earth, the interactions between methane, nitrogen, and other hydrocarbons could produce complex organic molecules. Such molecules are the building blocks of life as we know it, making Titan an exciting laboratory for studying probiotic chemistry. The secrets of Titan's methane lakes and the processes that sustain them remain locked within the moon's thick atmosphere and icy crust. Future missions, such as the planned Dragonfly rotorcraft, aim to delve deeper into Titan's mysteries, exploring its surface and atmosphere for signs of habitability or even alien life. For now, Titan stands as a reminder that our solar system is filled with worlds that defy expectations and challenge our understanding of what is possible. As we marvel at the alien beauty of Titan, our journey leads us to the icy plains and dynamic heart-shaped glacier of Pluto, a frozen frontier that surprises us with signs of geological activity in a world so far from the Sun. Now turning to the distant icy world of Pluto, we encounter a mystery as captivating as it is perplexing. the heart-shaped expanse known as Sputnik Planitia. This vast, bright region of nitrogen ice is not just a beautiful feature, it is an anomaly that challenges our understanding of planetary science. Despite Pluto's extreme distance from the Sun and its frigid temperatures, Sputnik Planitia exhibits signs of ongoing geological activity. How is this even possible on a world so small and cold, where one might expect nothing but a frozen, inert surface? One of the most intriguing aspects of Sputnik Planitia is its surface, which appears remarkably young. Unlike the heavily cratered terrains that dominate other distant bodies, this region lacks significant impact craters, suggesting it has been resurfaced relatively recently. This raises the question, what force or process is driving this renewal? Scientists speculate that the answer lies beneath the surface. It is believed that Pluto, against all odds, may harbor a subsurface ocean of liquid water kept from freezing solid by the heat generated from the decay of radioactive elements in its core. If this ocean exists, could it contribute to the movement and renewal of Sputnik Planitia's icy crust? Adding to the mystery is the chaotic flow of nitrogen ice across the glacier's surface. Observations from the New Horizons spacecraft reveal patterns of convection where solid nitrogen slowly rises, sinks, and flows over time, resembling the overturning motion of a boiling pot of water. This process, driven by Pluto's internal heat, is unlike anything observed elsewhere in the solar system and challenges our understanding of how even the smallest planetary bodies can sustain such dynamic behavior. There is also the question of the peculiar heart shape of Sputnik Planitia. Some scientists hypothesize that the glacier's unique form may be linked to the impact of a massive object long ago, an event that could have created a deep basin that later filled with nitrogen ice. Others suggest that gravitational interactions with Pluto's largest moon, Charon, influence the shape and distribution of the ice. But as detailed as these theories may seem, none provide a complete explanation, leaving the true story of Sputnik Planitia shrouded in mystery. Even its composition adds to the puzzle. The nitrogen, methane, and carbon monoxide ices that make up this region behave very differently under Pluto's extreme conditions compared to how similar materials act on Earth. The interactions between these exotic ices and the surrounding environment could hold clues not just to Pluto's geological activity, but to processes that might occur on other frozen worlds beyond our solar system. As we continue to unravel the enigma of Pluto's heart-shaped glacier, one thing becomes clear. Pluto, once thought to be a static frozen world, is a place of unexpected complexity and activity. Future missions may one day return to this distant frontier, diving deeper into its secrets and perhaps answering the tantalizing questions that remain. For now, as we leave behind the icy plains of Pluto, our journey takes us back across the solar system to the mysterious asteroid belt, a region of countless rocky remnants, and the perplexing question of why its total mass is far lower than we might expect. Now turning to the asteroid belt, a region that lies quietly between Mars and Jupiter, we find ourselves confronting a puzzle that has baffled scientists for decades. Why is its total mass so astonishingly low? Composed of countless rocky fragments ranging from tiny pebbles to dwarf planet-sized bodies, the asteroid belt might seem like a chaotic leftover of the solar system's formation. And yet, when we tally up the mass of all these objects, it amounts to just a fraction of 1% of Earth's mass, far less than what early models of solar system formation would predict. So, where did all the missing material go? One leading explanation points to the enormous gravitational influence of mighty Jupiter. Early in the solar system's history, as planets and other objects were forming, Jupiter's immense gravity likely disrupted the ability of material in the asteroid belt to coalesce into a larger planet. Its powerful gravitational pull scattered much of the mass outward into space or inward toward the Sun, leaving behind only a sparse collection of rocky remnants. In essence, the asteroid belt may owe its low mass to Jupiter acting as a cosmic gatekeeper, preventing the formation of a planet in this region. But gravitational disruption alone may not tell the whole story. Some scientists propose that during the chaotic early days of the solar system, massive collisions among protoplanets or planetesimals could have flung substantial amounts of material out of the asteroid belt entirely. These violent events may have ejected debris into interstellar space or sent it toward other regions of the solar system, explaining why the belt is far less dense than expected. If this is true, what could these collisions tell us about how planets like Earth and Mars acquired their current masses and compositions? Another possibility lies in the influence of the Sun's early activity. During the solar system's infancy, the young Sun likely emitted powerful solar winds and radiation bursts that may have stripped away lighter materials from the asteroid belt. Could these processes, combined with Jupiter's gravitational effects, have worked in tandem to strip the region of much of its original mass, leaving behind only the denser, rocky bodies we observe today? The asteroid belt's current composition also poses intriguing questions. While most of it consists of rocky and metallic bodies, we also find carbon-rich asteroids and even icy ones materials that suggest a complex history of migration and mixing. Did some of these objects originate in cooler, outer regions of the solar system and later migrate inward to join the belt? And if so, what can this tell us about the dynamic forces that shaped the early solar system as a whole? The mystery of the asteroid belt's low mass is more than just a question about missing material. It is a window into the chaotic processes that sculpted our solar system's architecture. Future missions to this rocky expanse hold the promise of shedding light on its enigmatic past, and perhaps even unlocking secrets about the origins of our own planet. With these questions in mind, let us now venture further into the solar system, where Saturn's moon Enceladus beckons us with another tantalizing mystery, the source of its remarkable water plumes. As the next challenge unfolds, we set our sights on Saturn's moon, Enceladus, a celestial body that has captivated scientists with one of the most intriguing discoveries in the solar system. Imagine this: towering jets of water vapor mixed with ice particles and organic compounds, erupting forcefully from cracks near the moon's south pole. These geyser-like plumes, first observed by the Cassini spacecraft, hint at something extraordinary beneath Enceladus' icy surface, a vast subsurface ocean kept in a liquid state by heat generated through tidal forces as Saturn's gravity flexes the moon's interior. But what makes these plumes truly fascinating is the question of what might be lurking in that subsurface ocean. On Earth, we know that life can thrive even in extreme environments like hydrothermal vents at the bottom of our oceans. Could similar conditions exist on Enceladus, with its plumes spraying clues into space? The presence of organic compounds in the plumes raises tantalizing possibilities. Are these just basic building blocks of life, or could they point to microbial ecosystems hidden miles beneath the ice? The more we study Enceladus, the more enigmatic it becomes. For instance, scientists still debate what powers these water plumes. Is it geothermal energy from the moon's core, or perhaps chemical reactions between water and rock at the ocean floor? And why are the plumes concentrated near the South Pole? Could this unique geographical activity provide insight into the hidden dynamics of Enceladus' icy crust and its interactions with the ocean below? Even more mystifying is the sheer scale of the phenomenon. Some estimates suggest that the plumes eject an astonishing small fraction of Enceladus' ocean into space each year. This cosmic fountain not only contributes to Saturn's faint E-ring, but also offers an extraordinary opportunity to study the moon's interior without needing to drill through miles of ice. Future missions could analyze these plumes in greater detail, possibly detecting signs of biological activity or providing a clearer picture of the ocean's composition and potential habitability. If Enceladus does harbor life, it would profoundly alter our understanding of where life can exist in the cosmos. No longer would we see Earth as an anomaly, but rather as part of a broader pattern in which life arises in unexpected corners of the universe. With its icy mysteries and signals of what could lie beneath, Enceladus stands as a beacon of hope in our search for extraterrestrial life. As we leave behind this ice-covered world of possibility, our journey now takes us farther into the solar system's history, where an ancient paradox surrounding the sun's early dimness and Earth's warm, watery conditions demands our attention. With the next phase of the journey in sight, we turn our attention to a question that reaches deep into Earth's ancient past, the faint young sun paradox. Imagine the sun not as the blazing celestial giant we know today, but as a much dimmer and cooler star during its youth, radiating significantly less energy. Based on what we understand about stellar evolution, this diminished energy output should have left early Earth as a frozen wasteland, incapable of supporting the liquid water that is essential for life. Yet the geological evidence tells a completely different story. Ancient rocks reveal unmistakable signs of flowing rivers, vast oceans, and warm, hospitable conditions billions of years ago. This paradox has puzzled scientists for decades. If the young sun wasn't warm enough to keep water from freezing, then how did early Earth sustain its liquid oceans? One widely discussed theory points to our planet's atmosphere as the key. Could it have acted like a thermal blanket, trapping enough heat to make up for the sun's lack of intensity? Some suggest that thick layers of greenhouse gases, such as carbon dioxide and methane, might have created a powerful insulating effect. Others propose that early Earth could have been home to unique atmospheric compositions or cloud patterns that reflected just enough sunlight to maintain temperate conditions. But even these hypotheses raise new questions. If methane, a potent greenhouse gas, played a central role, why don't we see evidence of it in the sedimentary record in amounts large enough to explain the warmth? And how do these atmospheric conditions fluctuate with Earth's evolving environment? Could volcanic activity or asteroid impacts have temporarily altered the climate, allowing liquid water to exist intermittently? Perhaps even more intriguing is the possibility that life itself could have contributed to solving this paradox. Early microbial life, if it existed in Earth's primordial oceans, might have interacted with the atmosphere in ways that stabilized the climate, creating a feedback loop that sustained warm conditions. This idea opens exciting avenues for understanding how life and planetary systems co-evolve. What makes this mystery so compelling is that it challenges us to rethink the delicate balance required for habitability. Solving the faint young sun paradox isn't just about understanding Earth's past. It's about unlocking secrets that could help us identify habitable exoplanets orbiting distant stars. If early Earth maintained liquid water under such challenging conditions, could similar mechanisms be at play elsewhere in the universe? As we marvel at this ancient puzzle, we're reminded that our planet's history is as complex as it is unique. Moving forward, we now set our sights on Mercury, where an entirely different mystery awaits. How can a small planet so close to the Sun sustain a magnetic field while its much larger neighbor, Venus, cannot? Let us delve into this enigma next. As the next challenge unfolds, we turn our gaze toward the innermost planet of our solar system, Mercury. Despite being a small, rocky world scorched by the sun, Mercury harbors a mystery that continues to puzzle scientists: its magnetic field. Mercury's magnetic field is surprisingly active, though much weaker than Earth's. The enigma lies not just in the fact that the planet has a magnetic field at all, but also in the question of why its larger neighbor, Venus, lacks one entirely. Here's why this is so intriguing. For a planet to generate a magnetic field, it typically requires a molten, metallic core that can produce the necessary electric currents through a process called the dynamo effect. Earth's strong magnetic field, for example, is powered by the movement of its liquid outer core. Now Mercury is small, so small in fact that its core should have solidified eons ago, extinguishing any potential for magnetic activity. Yet, evidence from spacecraft observations reveals that the planet's core is at least partially molten, keeping its magnetic field alive. Why this is the case remains one of the solar system's great puzzles. On the other hand, Venus, which is similar in size and composition to Earth, shows no sign of a magnetic field, even though its larger core should theoretically have the conditions needed to sustain one. Some researchers believe that Venus's extremely slow rotation, taking longer to complete one day than for the planet to orbit the Sun once, may hinder the dynamo process. But this raises another question. How does Mercury, which rotates even slower than Earth yet faster than Venus, manage to sustain its magnetic field? The mysteries deepen when we consider the Sun's role. Mercury's close proximity to the Sun exposes it to intense solar radiation and solar winds, which interact with and distort its magnetic field in fascinating ways. Could it be that the Sun's immense influence helps power Mercury's field, or does it simply complicate our ability to understand the phenomenon? Some theories suggest that Mercury's composition may hold the key. Its core makes up a much larger fraction of its volume compared to Earth's, possibly allowing it to retain enough heat to maintain partial fluidity. Alternatively, the magnetic field could be a relic of an earlier, more active dynamo phase, gradually fading but still detectable. Understanding why Mercury has a magnetic field while Venus does not isn't just about solving a planetary riddle, it's about uncovering the diverse ways planets evolve and interact with their environments. These insights could shed light on the conditions that make planets like Earth so unique. With Mercury's enigma in mind, let us now journey to Saturn's magnificent ring system to explore the mysterious origin of these celestial jewels. Why are Saturn's rings so strikingly prominent compared to the faint rings of other gas giants? The answers may lie hidden in their composition and history. Now turning to the breathtaking beauty of Saturn, we find ourselves captivated by its iconic rings, a feature unlike anything else in our solar system. These rings are extraordinarily bright, vast, and complex, stretching over hundreds of thousands of miles while remaining astonishingly thin, no more than 30 feet thick in most places. But their prominence raises a perplexing question. Why does Saturn have such striking rings, while the other gas giants like Jupiter, Uranus, and Neptune boast only faint and almost invisible ring systems? The composition of Saturn's rings provides some clues. Made mostly of water ice with small amounts of rock and dust, these rings reflect sunlight brilliantly, giving them their luminous appearance. However, this leads to an even deeper mystery. If the rings are primarily composed of ice, they should have darkened over time as they accumulated cosmic dust. Yet, their brightness suggests that the rings are relatively young in astronomical terms, perhaps only a few 100 million years old. So how did these icy structures form, and why so recently compared to the age of the planet itself, which spans over 4 billion years? One leading theory suggests a catastrophic event, perhaps the breakup of an icy moon or a passing comet that ventured too close to Saturn and was torn apart by its immense gravitational forces. This debris could have formed the rings we see today. Another possibility is that the rings might be remnants of the early solar system, leftover material that never coalesced into a moon. But if that's the case, why haven't Jupiter or the other gas giants retained similar features over billions of years? The ongoing mystery deepens when we consider the role of Saturn's gravitational field. Its massive gravity not only shapes the rings into defined bands, but also creates gaps and patterns within them through the influence of its numerous moons. These moons, known as shepherd moons, interact with the rings in fascinating ways, herding particles into narrow streams and maintaining the structure's intricate beauty. Could Saturn's unique collection of moons have played a key role in sculpting its rings into their current form? another question scientists are exploring is the durability of the rings. Observations from the Cassini spacecraft revealed that Saturn's rings are losing material at a rapid rate, with icy particles falling into the planet's atmosphere in what scientists have termed ring rain. This means the rings might be temporary, potentially disappearing entirely within a few 100 million years. Are we witnessing a fleeting stage in Saturn's long history, one that other gas giants may have experienced and lost before we were able to observe them? Understanding Saturn's rings is about more than solving a cosmic puzzle. It's a window into the forces and events that have shaped not only our solar system, but also planetary systems around other stars. As we marvel at their striking beauty, we are reminded of the dynamic and ever-changing nature of the universe. With the mysteries of Saturn's majestic rings still shimmering in our minds, let us now set our sights on a peculiar anomaly that baffled scientists for decades: the unaccountable trajectory shifts of the Pioneer spacecraft as they ventured into the vast expanse beyond our solar system. As the next challenge unfolds, we find ourselves drawn into the uncharted regions of the solar system, guided by two remarkable explorers, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these spacecraft were among humanity's first attempts to venture beyond the familiar realms of our planetary neighborhood. Their mission was to study the outer planets and then continue their journeys into interstellar space, carrying with them golden plaques inscribed with messages intended for any extraterrestrial beings they might encounter. While their scientific achievements were groundbreaking, their final journeys have left scientists with one of the most intriguing mysteries in modern space exploration. As Pioneer 10 and 11 traveled through the solar system, their trajectories began to exhibit slight but consistent deviations from what scientists had meticulously calculated. These spacecraft, traveling hundreds of millions of miles from Earth, seemed to be experiencing an unknown force, tiny but measurable, pulling them back toward the sun. The anomaly was first noticed in precise tracking data, which revealed that the spacecraft were slowing down ever so slightly, contrary to predictions based on known physics. This puzzling phenomenon, now famously dubbed the Pioneer anomaly, has sparked decades of debate and investigation. One of the first explanations considered was that something mundane might be causing the deviation. Could it be tiny gas leaks from the spacecraft themselves, gently pushing them off course? Or perhaps an uneven emission of heat from their radioactive power sources, creating a subtle recoil effect? These explanations seemed plausible, but attempts to model the precise impact of these factors failed to fully account for the observed discrepancies. The mystery remained. Another possibility was that our understanding of gravity itself might hold the answer. Could the anomaly be hinting at flaws in our current models of physics, perhaps revealing a previously unknown aspect of gravitational interactions at great distances? This idea was tantalizing, as it could offer insights into phenomena like dark matter or modifications to the laws of gravity. However, such theories have not gained widespread acceptance, and the data from the Pioneer spacecraft remains inconclusive. Some scientists have also pondered whether the anomaly could be attributed to forces external to the spacecraft, perhaps interactions with the solar wind, dust particles, or other environmental factors in the far reaches of space. But once again, these hypotheses have not provided a definitive explanation for the precise and consistent nature of the anomaly. Even with a wealth of data from both spacecraft, the Pioneer anomaly remains unresolved, and the spacecraft themselves are now too distant for further tracking. Their signals have long since faded, leaving behind only questions and speculation. The Pioneer missions remind us that even our most advanced technologies can encounter mysteries that challenge the boundaries of human knowledge. As we ponder the enigmatic forces influencing these silent explorers, our journey through the curiosities of the solar system takes yet another turn. Now, let us shift our focus to the origins of our own closest celestial companion, and unravel the lingering questions surrounding the formation of the moon. As the next chapter of our journey unfolds, we turn our gaze to the night sky and focus on a celestial companion that has inspired wonder for millennia, the moon. Its presence is a constant in our lives, yet its origins remain one of the most debated mysteries in planetary science. How did this luminous body come to be? To answer this question, scientists have developed several theories, each offering intriguing insights while leaving certain puzzles unanswered. The leading explanation, widely known as the giant impact hypothesis, suggests that billions of years ago, a Mars-sized body, often referred to as Theia, collided with the young Earth. The immense energy of this collision would have ejected a massive amount of debris into orbit around our planet. Over time, gravity worked its magic, coalescing this material into the moon we see today. This theory accounts for many observations, such as the moon's relatively large size compared to Earth and the similarities in their isotopic compositions. However, it also raises questions. For instance, if the moon formed from a mix of material from both Earth and Theia, why does its composition appear so similar to Earth's mantle, with barely any trace of Theia's material? This discrepancy has left scientists scratching their heads. Another theory posits that the moon formed independently in the early solar system and was later captured by Earth's gravity. While this idea might seem plausible at first glance, it struggles to explain the chemical and isotopic similarities between the Earth and the moon, which suggest a shared origin rather than an independent one. A third hypothesis suggests that the Earth was spinning so rapidly in its early days that part of its molten material broke away to form the moon. This concept, known as the fission theory, could explain the moon's composition but fails to account for the dynamics required to eject such a large amount of material into space. Modern computer simulations have not supported this scenario as a likely explanation. More recent variations of the giant impact hypothesis attempt to address some of these issues. Some scientists propose that multiple smaller impacts rather than one massive collision could have gradually built the moon. Others suggest that the impact might have vaporized Theia entirely, leaving behind only Earth's material to form the moon. These updated models are compelling but still lack definitive proof. Then there is the question of the moon's early history. Its formation was likely followed by a period of intense volcanic activity and the creation of its now familiar surface features, such as maria and craters. But why did this activity cease, and how exactly did the moon's surface cool and solidify over time? These are questions that remain open to exploration. As we look at the moon today, it serves as both a reminder of Earth's tumultuous past and an enduring enigma of its own. The moon's formation is a puzzle with many pieces still missing, and while science has come far in piecing together its story, the complete picture continues to elude us. And as the mysteries of the moon linger in our minds, we now venture into even more uncharted territory, turning our attention to the enigmatic interstellar visitor that briefly graced our solar system, Oumuamua. Now turning to one of the most intriguing visitors our solar system has ever encountered, we arrive at the mystery of Oumuamua. Discovered in 2017, this peculiar object was the first interstellar visitor ever detected passing through our celestial neighborhood. Its name, which means scout or messenger in Hawaiian, hints at its enigmatic nature, and even now, its true identity remains a subject of heated debate. At first glance, scientists thought Oumuamua was a comet, but it lacked the typical tail of gas and dust that comets usually display as they approach the sun. Then came the idea that it might be an asteroid, a rocky body wandering across the cosmos. However, its unusual elongated shape, estimated to be roughly 10 times longer than it is wide, doesn't match what we usually see in asteroids. To complicate matters further, Oumuamua exhibited a mysterious acceleration as it exited the solar system, as though something unseen was giving it an extra push. This behavior perplexed researchers as it did not align with gravitational interactions alone. One explanation is that this acceleration might have been caused by outgassing, where volatile materials on its surface were released, creating a tiny thrust. But without the visible signs of gas usually seen in comets, this theory is far from conclusive. Interestingly, some scientists have even speculated that Oumuamua could be something entirely unprecedented, perhaps a fragment of a shattered planet from a distant star system, or even an artificial probe sent by an advanced civilization. While such theories capture the imagination, there is currently no evidence to support them. What makes Oumuamua even more puzzling is that it appeared and disappeared so quickly, giving scientists only a brief window to observe and collect data before it vanished beyond the reach of our telescopes. This fleeting encounter left us with more questions than answers about Oumuamua's origins, composition, and purpose. Could it represent a common type of interstellar object that we've simply never had the chance to study before? Or is it a rare enigma, a one-of-a-kind messenger from the unknown? As we gaze back at the path it took and ponder its mysteries, Oumuamua reminds us of how much remains to be discovered about the nature of our universe. And just as this interstellar visitor fades from view, we turn our focus toward another enduring riddle, this time found closer to home: the mysterious resurfacing of Venus, a planet that holds secrets as shrouded as its thick, cloud-covered atmosphere. Now turning to the mysterious surface of Venus, we encounter a planet that defies expectations in more ways than one. Despite being similar in size and composition to Earth, Venus presents a fascinating enigma. Its surface has far fewer craters than scientists would predict for a planet of its age. Typically, celestial bodies accumulate craters over billions of years from impacts with asteroids and comets. However, Venus seems to have undergone a dramatic transformation that wiped much of this record clean, leaving a relatively young and smooth surface. This raises a compelling question: what could have caused such an extensive resurfacing event? One leading theory involves volcanic activity on a massive scale. Venus is known for its extreme volcanic landscape, with vast lava plains, towering shield volcanoes, and features that suggest eruptions may have played a key role in reshaping its surface. Some scientists propose that at some point in the planet's past, widespread volcanic activity could have covered older, cratered terrain with fresh layers of molten rock, effectively pressing the reset button on its geological timeline. Another possibility lies in tectonic activity, although Venus lacks the plate tectonics we see on Earth. Instead, its surface may experience periodic bursts of geological upheaval, where heat from the planet's interior builds up and is suddenly released in a catastrophic event. Such a process could resurface vast areas at once, erasing the scars of ancient impacts and creating the young-looking terrain we observe today. Adding to the complexity is Venus' thick, toxic atmosphere, composed mostly of carbon dioxide and laced with clouds of sulfuric acid. This dense blanket exerts immense pressure on the planet's surface, which could influence geological processes in ways we don't fully understand. It's also possible that chemical interactions between the surface and the atmosphere accelerate the erosion or masking of craters, further complicating our efforts to unravel this mystery. Even with these theories, a definitive explanation remains elusive. Venus' scorching temperatures and crushing atmospheric pressure make it one of the most challenging places for spacecraft to explore, limiting our ability to gather detailed data. Future missions equipped with advanced technology may one day unlock the secrets hidden beneath its thick clouds. For now, Venus stands as a vivid reminder of how much we have yet to learn about planetary evolution. What could these resurfacing events tell us about the broader dynamics of rocky planets, including our own Earth? As we ponder these questions, we move on to explore another planetary puzzle: the supersonic winds of Neptune, which challenge our understanding of atmospheric physics in the outer reaches of the solar system. As the next challenge unfolds, we find ourselves drawn to the distant and icy realm of Neptune, a planet that holds one of the most perplexing atmospheric mysteries in the solar system. Despite being so far from the Sun, where solar energy is weak and temperatures plunge to unimaginably cold levels, Neptune is home to some of the fastest winds ever recorded. These supersonic winds can reach staggering speeds of over 1,200 miles per hour, a phenomenon that defies our current understanding of atmospheric dynamics. Scientists are left wondering what powers these ferocious winds on a planet that receives such limited energy from the Sun. One possible explanation involves the planet's internal heat. Unlike Uranus, Neptune emits significantly more heat than it absorbs from the Sun, suggesting an active interior that might drive powerful atmospheric currents. This internal heat could create strong temperature gradients, fueling intense wind patterns that rip through the planet's upper atmosphere. Another layer of complexity arises from Neptune's unique atmospheric composition. The planet's atmosphere is primarily made of hydrogen and helium, along with traces of methane, which gives it its signature blue hue. Methane absorbs red light, but its role in the energy dynamics of the atmosphere remains poorly understood. Could interactions between these gases contribute to the extreme winds, or is there an unknown factor at play, perhaps related to the deeper layers of the planet that we have yet to explore? Adding to the enigma, Neptune's winds don't just move fast, they also exhibit unusual stability. Some storms on Neptune, like the famed Great Dark Spot observed by the Voyager 2 spacecraft, appear to persist for long periods, even in such a chaotic and energetic environment. How these storms form and maintain their structure remains an open question, one that challenges our understanding of fluid dynamics and weather systems on gas giants. Complicating matters further is the planet's immense distance from Earth. Observing Neptune requires powerful telescopes and innovative techniques, as only one spacecraft has ever visited the planet. The Voyager 2 mission provided invaluable data, but much of Neptune's atmosphere remains shrouded in mystery, awaiting future missions to unlock its secrets. Neptune's fast winds are a vivid reminder that even in the coldest, most remote corners of our solar system, dynamic processes can unfold on a scale that challenges our imagination. What drives these winds, and what can they teach us about the atmospheres of other giant planets, both in our solar system and beyond? As we marvel at Neptune's ethereal beauty and atmospheric extremes, we turn our attention to the final unsolved mystery on our list, the elusive nature of dark matter and its minimal impact within the solar system. As the Sun rises on the next chapter, we journey into one of the most profound enigmas, not just of the solar system, but of the entire universe, the bewildering mystery of dark matter. Dark matter is thought to make up most of the mass in the universe, yet it remains completely invisible, detectable only through its gravitational effects. Galaxies, including our Milky Way, seem to be enshrouded in this mysterious substance, as its immense gravitational pull holds these vast cosmic structures together. But here's where things take a puzzling turn. Within our own solar system, dark matter appears to have an almost negligible impact. This raises a critical question. If dark matter dominates the universe on a larger scale, why does it seem to barely register on a smaller scale like our solar system? Scientists have long speculated about the nature of dark matter and its interaction, or lack thereof, with ordinary matter. One possibility is that dark matter's density is so low in our immediate vicinity that its effects are simply too subtle to detect against the overwhelming gravitational forces of the Sun and planets. Another idea is that dark matter interacts with normal matter in ways we have yet to understand, potentially involving exotic particles that pass through ordinary matter without leaving a trace. Efforts to directly detect dark matter on Earth have so far been met with silence, leaving researchers to rely on indirect evidence gathered from astronomical observations. And while these observations clearly show dark matter's influence on galactic scales, they struggle to explain why its presence seems so faint within the boundaries of our solar system. Could this mean that dark matter behaves differently in denser, more localized environments? Or are we missing a key piece of the puzzle that could redefine our understanding of the cosmos? Adding to the intrigue, theoretical physicists have proposed radical ideas about the nature of dark matter. Some suggest it could consist of invisible particles unlike anything found in the standard model of particle physics, while others speculate it might not be matter at all, but rather a manifestation of new forces or dimensions we have yet to discover. These possibilities not only challenge our current understanding of physics, but also hint at the potential for groundbreaking discoveries that could forever alter the way we perceive the universe. The dark matter problem isn't just a question for astrophysics, it's a question for humanity. Understanding what dark matter is, how it behaves, and why it seems so elusive within the solar system could unlock secrets about the origins and fate of the universe itself. As we continue to refine our tools and theories, this unsolved mystery stands as a testament to the vastness of what we have yet to learn. With the next phase of the journey in sight, let us take a moment to reflect on the 25 unsolved mysteries of the solar system that we have explored together. From the enigma of the solar system's formation to the elusive nature of dark matter within our celestial neighborhood, each mystery reveals just how much there is still to uncover about the universe we call home. These puzzles, ranging from the puzzling behavior of Venus's retrograde rotation to the breathtaking water plumes erupting from Enceladus, remind us of the fascinating complexity that lies within our own cosmic backyard. They challenge our understanding, ignite our curiosity, and push the boundaries of what we thought we knew. As we wrap up this incredible exploration, think about which mystery resonated most with you. Was it the strange case of Neptune's supersonic winds, or perhaps the tantalizing hint of life supporting conditions on distant moons like Titan? These unanswered questions are more than just scientific curiosities. They are a testament to humanity's unyielding drive to seek the truth, to venture further, and to unlock the secrets of the universe. If you are as captivated by these cosmic enigmas as we are, let us continue this journey together. Share your thoughts on the mystery that intrigued you the most in the comments below, and let us know what you think the answers to these questions might be. Don't forget to subscribe to our channel and hit the notification bell so you never miss another deep dive into the wonders of space. And as always, thank you for joining us on this adventure. The universe is vast, and the answers we seek are out there, waiting to be discovered. Until next time, keep looking.